In this video, we're going to look at how to build a reduction table using experimental data. There are two kind of problems you'll see here. This is the first type where you're given a data table from an experiment. So we're going to walk through this data table and then go through how to interpret and solve the question ranking the oxidizing agents from strongest to weakest. So first of all, we need to know which of these species are oxidizing agents. Typically, metal atoms, so I'm highlighting these across the top row. These are typically reducing agents because they readily give up electrons to form cations. And if you look on the rows down the side, we have their charged counterparts. These are the oxidizing agents. Now, we can look and see how many times a given species reacts. The more times an oxidizing agent reacts, the stronger it is. So, I'm going to add a little column at the bottom. And if you look at the key here, we see that a check mark means there was a spontaneous reaction, and X means there wasn't. So if we go across from palladium down to iridium, we see palladium 2 plus had 2 reactions. Zirconium 4 plus had 0. Indium had 1, and iridium had 3. That tells us that iridium is our strongest OA, and zirconium is our weakest. So in terms of ranking these, we know that iridium 3 plus is our strongest, followed by our 2 reaction, palladium 2 plus, then indium 3 plus, and lastly, zirconium 4 plus. So that's one type of problem. The other type of problem you'll see is one more like this, where you're given a list of reactions and asked to rank that way. So we're going to walk through this. The little spiel at the top is not really important here. So we're going to look and we're going to say, okay, our first reaction was cobalt 2 plus and neodymium. Now cobalt 2 plus is a cation. It's likely that cobalt 2 plus is our oxidizing agent. Neodymium here would be our reducing agent. In our second reaction, our metal atom, neodymium, again is a reducing agent. Yttrium 3 plus would be an oxidizing agent. And then samarium 2 plus would be an oxidizing agent, and yttrium solid would be a reducing agent. So of our chemical species listed, this was originally a numeric response. Our oxidizing agents, I'm just going to highlight their numbers in red, are these 4 species, meaning that we can basically ignore our metal atoms. So we're going to rank 5, 6, 7, and 8 from strongest to weakest. So we need to look at our experimental data. Now we know from our table that if a reaction is spontaneous, the oxidizing agent is above the reducing agent. So we're going to use our reactions to build a table. The first table, or the first reaction we're going to look at is cobalt and neodymium. So cobalt 2 plus and neodymium have a spontaneous reaction, meaning that cobalt 2 plus in our reduction table is somewhere above neodymium. So I'm going to leave a little space in case I need to put something in between them. So I've done the first reaction, so now I'm going to move to the second. We see that neodymium is not a strong enough reducing agent to reduce yttrium 3 plus, meaning that yttrium 3 plus is somewhere below neodymium. And our third reaction, we have samarium and yttrium, neither of which are directly on our chart. However, yttrium 3 plus will be reduced to yttrium with the addition of 3 electrons. So they're going to be horizontal from each other on this chart. And so we know that samarium 2 plus is going to be below yttrium. And so we could fill in the rest of our table if we wanted a complete reaction here. Neodymium 2 plus and cobalt to cobalt. So we could write a complete table if that's what we were being asked to do. However, here we are just being asked to rank from strongest to weakest. So our strongest oxidizing agent is cobalt 2 plus, followed by neodymium 2 plus, then yttrium 3 plus, and finally samarium 2 plus. So that's the second type. It's a little bit more complex, but if you just try to rank them, leave yourself some space, it's not too bad.